So, welcome back to my lectures on groups, rings, and fields. Our next topic is on rings of polynomials. Rings of polynomials. So, before we start this topic, I would like to give a very brief introductions to rings. It is another algebraic structure, just like group theory, groups. So, we'll give a very brief introduction to rings and the related structures like integral domain and fields and etc. So, we started the definition of group with an objective of solving a monic polynomial like this: x plus a is equal to b. We'll take a number here. X plus 3 is equal to 5. So our objective was to find the value of x in the same domain as 3 and 5. These are integers, or you can consider that as a real number or complex number or rational number. So in order to find the value of x in that group or set or the domain of values, we found that we need to have an identity, and we need to have inverse for all elements. Of course, we should have a binary operation, and that is why we should have identity and inverse, and we also should have an associative property. Valid associative property. With these four ideas in mind, we started developing a structure called group. See, this is a monic polynomial, monic linear polynomial. We haven't defined polynomial yet. We'll come there later, but this polynomial that what I'm saying is the idea we have it on polynomial in your elementary algebra session. We'll formally define what a polynomial later. Or you can say linear equation if you want to make it more convincing. Linear equation. Monic means the coefficient of the variable is 1, meaning it is the identity of, it is not identity, it is just 1. There is no other coefficient that can have here. Linear means the maximum power of the variable is 1. So this is the kind of equation we are trying to solve, and we found that we could come up with a structure called group which has got these properties. Now we are going to make it little bit more complicated like this. For example, we'll say ax plus b is equal to c. Well, this a is not the number of times x is added. So if he says in group, if you say 5x, meaning it is actually means that it has to be an integer. So it means that x plus dash dash x 5 times. This is not what I'm talking about here. This is an element in the algebraic structure we are going to define. It could be a complex number, it could be a rational number, real number, or anything. So our objective is to find the value of x. That is where we come up with a different structure, rings. Here you need only one binary operation. Here we have two operations. One is this, and another one is the multiplication. This we call it as addition, and we call this one as multiplication. So in the new structure, we have two binary operations. Well, when we are going to define a ring, that is not sufficient enough to solve this, but it is going to be a generalized version of the structure we are looking for. The final algebraic structure for which we can find a solution for this equation is called field. We'll come to that later. Field is a very specialized ring. Ring is more generalized. So we are going to define a ring here, and finally when we come to define the field, then we'll come to know that why we defined like this. First of all, let R be a non-empty set with two binary operations. We call it as addition and multiplication. With the following property. With the following properties. The first property is that R along with the addition should be, or that is a abelian group, commutative group. Okay, that is the first property. The second property is multiplication is associative. That implies A times B times C is equal to A times B times C. And the third property is multiplication is distributive over addition, in the sense that A times B plus C is equal to AB plus BC, and A plus B times C is equal to AC plus BC. If these three conditions are satisfied, then R along with addition and multiplication is a ring. We are going to give you a lot of examples on rings, so it will be very clear once you get all kinds of different rings. So that is a definition of a ring. Before we come to the examples, we need to note that a ring does not need to have a multiplicative identity. A ring does not need to have a multiplicative identity. So we'll come up with a ring which has got a multiplicative identity, which will come up with a ring which does not have a multiplication identity. Okay. Another property, not the property, another thing which we need to note down is multiplication does not need to be commutative. That means AB does not need to be BA. Okay. Now, if a ring has a multiplicative identity, it is called a ring with unity. A ring with the unity. And if a ring, if multiplication is commutative in a ring, it is called a commutative ring. Okay. Now let us take examples. First set of examples, very simple. Z plus the multiplication, then Q plus multiplication, R plus multiplication, and C plus multiplication are examples of commutative ring with unity. Okay, and they are all infinite. Now Z comma plus addition and multiplication is a commutative ring with unity, but if you take an NZ or probably let us say 2Z is also a ring is also a commutative ring with no unity, because 1 does not belong here. All other ring properties are valid, but 2Z does not have unity. Now, let R be a ring. Then M and R with the addition and multiplication. This is actually the collection of all n by n matrices with entries from R. So this could be either Z or Q or R or anything. Then M and R with the addition and multiplication, matrix addition and matrix multiplication, is a non-commutative ring with unity. Okay, we'll do some more examples. Let us take another example. Let f is a set of all functions from R to R. This is a real valued function. Then f plus is a ring with the following definitions. Meaning you need to define what is addition and what is multiplication. So f plus g of x is equal to f of x plus g of x. That is how we define the addition. And f g of x, f times g of x, is equal to f of x times g of x. This is not composition. This is point-wise multiplication. So if you define like this, then f addition and multiplication is a ring. So these are all infinite rings. Let us come up with a finite ring example. Let us take Zn with the addition as addition modulo n and multiplication as multiplication modulo n. Let us take an example here. Z4 0 1 2 3. So you know that Z4 plus is a group, so you don't need to worry about it. It's a group that you already seen that. multiplicative modulo m, and means here if you take any two elements, let's say 2 times 3 is actually modulo 4 is 2, mod 4, and that belongs here. See, when we say that multiplication is a binary operation, that means that it should be closed in that. It cannot go outside of C4. So if you take any multiplication, and find the modulo of 4, then that number will belong to Z4. So Z4 with the plus and multiplication modulo n or modulo 4 is a Now let us do some more definitions. The unity of a ring R is its multiplicative identity. A ring does not need to have a unity. A ring with unity is called a ring with unity. A ring with a multiplicative inverse. The multiplicative inverse is called, multiplicative identity, is called a ring with unity. A ring with the multiplicative identity is called a ring with the unity. Example, z plus dot is multiplication, is a ring with unity. But 2z or 3z plus is a ring with no unity. Okay. Next definition is an element in a ring R is a unit. This is unity and this is unit. If it is non-zero and has a multiplicative inverse. A zero element does not have a multiplicative inverse. We are only considering non-zero elements of R. Zero means it is an identity of addition. Now, if every non-zero element of a ring R is unit. If every non-zero element is a unit, then R is called a division ring. Example, Q is a division ring, but Z is not a division ring, because Z contains only integers except one. None of the non-zero integers have a multiplicative inverse. Okay. Another definition is a commutative division ring is called a field. So that means in a field multiplication is commutative and every non-zero element of the field has a multiplicative inverse. So Q plus the multiplication is a field, but Z is not a field. We'll have a couple more definitions. A subset of a ring R is called a subring if that subset is a ring by itself with the induced binary operations. Example, Z plus is a subring of Q plus, which is a subring of R plus which is subring of complex numbers. Similarly, a subset of a field is called a subfield if that subset is a field by itself with the induced binary operations. So Q is a subfield of R, which is a subfield of C. Okay. Some simple properties of a ring. I'm not going to prove this, it's all very simple, but we are going to use it, so don't get confused. So let me write down those properties. Properties of a ring. 1. A times 0 is equal to 0 times A is equal to 0. 2. A times minus B is equal to minus AB, is equal to minus A times B. And the third one is minus A times minus B is equal to A. So very simple to prove, but remember when I say minus B, that implies it is the additive inverse of B. That is the meaning of minus B. Okay, so we should only, when we establish this result, we should only use this property of addition here. Okay, so I'm going to leave this as an exercise for you to prove this. All very simple, but we'll use this in our discussions later. Now, next definition is homomorphism. We have defined homomorphism for groups. So now let us define the homomorphism for a ring. So let R and R prime be two rings. A map phi from R to R prime is a homomorphism if phi of A plus B is equal to phi of A plus phi of B, and phi of AB is equal to phi of A times phi of B for all A comma B in R. In group homomorphism, we have only one condition. In ring, we have two binary operations, so we have to have two conditions on homomorphism. It actually ensures that the elements of R and the image of the homomorphism behaves exactly similar. If phi is a bijective homomorphism from R to R, then it is called an isomorphism. Give one example of very useful example. We are going to use this example in a lot of places. So let F be the ring of all real valued functions. And phi of A from F to R for some A in R defined by, this is real value, defined by phi of A of F is equal to F of A is a homomorphism. Okay, homomorphism, and is called evaluation map. Another example of isomorphism is let phi from Z to 2Z by phi of n is equal to 2n, then 5 is an isomorphism. I'm going to leave all these for verification as an exercise. Verify both.